Hi, my name is Matt Duff. I'm an application engineer covering precision amplifiers, specifically instrumentation amplifiers. And today we're going to talk about how to use a Sallen-Key configuration to create complex poles. So, the most common way to, or what we learned last time, is if you just try to use real pole filters, so just kind of standard RC filters gained together, you end up getting too much attenuation near your cutoff frequency. So what you really need is some sort of system where you can get less attenuation near your cutoff frequency. And the way to do that is to use complex poles. And a very common configuration, not the only configuration, there's plenty of other configurations out there, but a very common configuration to do that is called the Sallen-Key configuration. So if we want to draw the Sallen-Key, and the Sallen-Key is pretty popular, I think mainly because it's the minimum number of components that you need in order to create your complex pole. So Sallen-Key creates a two-pole complex pole system. Okay, so let's analyze how this works. Let's look at the low frequencies, high frequencies, and so forth. So at low frequencies, we can see that these capacitors are going to be open. Let me just call these, so for future reference here, label these. So at low frequencies, these capacitors are open, and you can see this is just a buffer amplifier configuration. And at high frequencies, you can see that these capacitors are going to be shorts, and so if any signal that comes through here is going to be shorted by the C2. In fact, this is shorted by the C2, so my output voltage at high frequencies is very small. So we can kind of view this output voltage as a virtual ground. And because that's a virtual ground, if I look in from my input, I can see here's one filter, so formed by this R1 and C1, going to this kind of virtual ground, and here's my second filter. And so that's how I get this dual pole action. So if I draw what we've learned so far at low frequencies, I'm just this DC gain of 1, and at high frequencies I have this nice attenuation at 40 dB per decade. But in the middle is where the interesting thing happens. And the way we make it interesting is we actually use positive feedback. So, you learned in school, be careful with positive feedback. It's dangerous. It can cause you to oscillate and so forth, and that's true. But sometimes it can actually be helpful. So we have this positive feedback that goes from our output through C1 back to our input here. And depending on how much we let through this C1, we can create different behavior here at our input. So let's say that our capacitors are the same type of value. So let's say my resistors are the same and my capacitors are the same. Then I'll get this pretty lazy roll-off where my cutoff frequency, I'm going to be, say, my cutoff frequency, I'll be at 6 dB down. But if I make my capacitor bigger, then I can change my the behavior here in the middle. So I can make it something like this, or if I make my C1 a lot bigger than C2, I can create this really big peaking. And so by having this flexibility, I'm able to create something that looks a lot more like a brick wall filter. And in fact, now what I can do is I can gang multiple of these stages together. So, if I take this and I make another one, so I have a 4-pole filter, I can make something even more like a brick wall. And I'm sure you've probably heard about these terms, Butterworth, Chebyshev, and so forth. And really all what those are is I'm taking different cues, or different peaking values, and different cutoffs and combining them together. So let's say I have one filter that looks, one stage that looks something like this, and I have another stage that maybe looks like this, and I have another stage that looks like this. And when I combine them all together, all of these stages, then I get something that looks almost like a brick wall. And how I set this peaking and these cutoffs is determined by these different Chebyshev and Butterworth filter coefficients. We're not going to actually go into the differences of those, but I do want to cover the equations for setting the Q, which is this peaking, and the cutoff frequency of this system. So first, the cutoff frequency is pretty easy to remember. So if you remember for our one-pole system, our cutoff frequency is just 1 over 2 pi RC. And for this Sallen-Key filter, our cutoff frequency is 1 over 2 pi square root of R1, R2, C1, C2. So you can see that if R's are the same and C's are the same, it simplifies down to that one-pole filter equation. So that's pretty easy to remember. The one that's a little bit harder to remember is actually the equation for Q. So this is FC. The equation for Q, we have our square root of R1, R2, C1, C2. But then we have R1 plus R2, C2. And this Q is just a measure of how high I peak. So if I had a Q of 10, that means that my peaking is 10x higher than what I've got here. If I have a Q of 1, that at this cutoff frequency, I've got basically 1x what I've got here. You'll notice from this equation that the bigger I make C1, just like we said, the bigger my Q gets. One other thing to mention here, another way that you can change your Q, you may see sometimes, is I can actually add some DC gain to the circuit by adding these couple of resistors here. And by adding this DC gain, I create a bigger voltage at this V out, and so I send more voltage back to my input. So this is another way that I can manipulate my Q that you may see. So that's the basics of how a Sallen-Key filter works.